Welcome to Chapter 1, Section 4, Day 2. Let's look at the properties of continuity. See if you can find this on your note sheet. It's on the top of a page on the back side. And there are certain functions that behave very nicely, and we just know that they're going to be continuous. But they're continuous with a little bit of contingency here for the points that sit in their domain. So keep that in mind. Polynomial functions behave very nicely. They're nice, smooth, continuous curves. They are continuous everywhere. And for the most part, any value, any real number will be in their domain. You know, when we're looking, what is a polynomial? Think about, something nice like this. Going to behave really nicely. I have no denominator, so I really don't have any spots I have to be careful of for excluding out of the domain of all reals. Next one, let's move on to rational functions. Rational functions, notice that they look like a fraction, right? It's a ratio, kind of two polynomials. And this one we do have to be careful because the polynomial that sits in the bottom could have some locations where the x value would take it to 0. Let me just write out a simple rational function. So 5 over 3x. Well, this thing will be continuous everywhere except I could not let x be 0. So everywhere else it's going to be continuous, but not at x equals 0 because that's not part of its domain. And a third type of function to discuss is the radical function, such as the square root of x would be one example, or the cube root of x. The square root of x, we know that x could not equal, I should have this a little differently, shouldn't be less than 0 because then I'm into negative numbers, which would take me into imaginaries, and we're only working under the real number line system. So everywhere else where x is greater than 0, I'm going to have a continuous function given it's a radical like a square root function there. And finally, the trigonometric functions, they are continuous everywhere as long as we are staying within their domain. So for sine and cosine, those nice smooth, sine and cosine waves, they're continuous on all reals. Tangent, though, remember there's asymptotes involved in the tangent function, that graph, and you have places of discontinuity at negative pi over 2 and pi over 2. So there are some spots with trigonometric functions where the domain has restrictions. So by combining some theorems together, we get this summary that we can conclude there's actually a wide variety of elementary functions like those that are continuous at every point in their domain. So remember, there's that qualifier. Look at intermediate value theorem. And this is an important theorem. We will be working with this one throughout the year. Sometimes you may hear it referred to as the IVT, the Intermediate Value Theorem. So if I think about what the word intermediate means, it means in between. It's intermediate, like grades 10 and 11 are intermediate grades. They're sitting between, in high school, they're sitting between your freshman year and your senior year. So intermediate values. The theorem reads, if f of x is continuous on a closed interval, remember these brackets mean I will include my endpoints, on a closed interval a to b, and there is a value k that sits between f of a and f of b. So I'm thinking these are y values, right? When I plug in a, I get out some y value, and when I plug in b, I get out a y value. Then there is at least one number c in the closed interval a to b such that f of c will turn out to equal k. Now, let's break this theorem down. Pause it and reread it, might be helpful for you. Remember in geometry when we wrote if-then statements, we made you identify the hypothesis and we made you identify the conclusion. So that's what we're going to do here. And the hypothesis on this actually has two parts to it. So if f of x is continuous on the closed interval and k sits between, there's a two-part hypothesis to this. So one is that it is continuous, it is a continuous function on the closed interval a, b. The second thing is I have to see that k resides between f of a and f of b. It may be that k is larger than f of a but smaller than f of b, or it could be just the reverse where f of b is the smaller value and k sits between it and underneath f of a. So either scenario can be fine. The conclusion is then there's at least one number c in the closed interval. Conclusion, there is at least, could be more, but there's at least one number, the c value, in the closed interval a to b such that, and that's what ST is going to stand for, such that f of c equals my k value that I was talking about. Well, what does this look like? I think a picture might help explain this theorem quite well. So I have this f function and I note that it is continuous on my interval from a to b. Okay, so I have the first part of my hypotheses. Secondly, I need to check this k value that I'm going to go after sits between f of b and f of a. And it does here, doesn't it? Look how, so I'm really interested, let me grab the highlighter. I'm interested in this region of my curve where I have a and b. And now I note that I have this k value that falls in the range between f of a and f of b. In fact, it appears that k is smaller than f of b and it's larger than f of a based on our diagram here. So what this theorem is suggesting is that there is a, if there is this k value that sits between it, then I should be able to find a corresponding c value for x that resides between a and b. It's almost like it guarantees it, isn't it? If k sits between f of a and f of b, then there must be a c value, or I can find an x that is going to be between a and b. Okay, it gives me this range of values to look for to find that c value, so that when I plug in c into my function, it's going to turn out to be come out with this k value, and I can be guaranteed that k sits between f of a and f of b. The next picture is really just identifying the fact that, you know what, it can happen that there is more than one. This says there is at least one, but here I can see there actually are three k values. Look at, if we draw a horizontal line across from k there, I hit it 1, 2, 3 times within the band where x sits between b and a, and this would be my c value that I'm looking for. Well, there's actually 3 different c values on this one. So there's at least one. Now, why is it necessary that our function be continuous? Well, if it weren't continuous, look at this one where we get this break in our function. I might just so happen to choose a value, a y value, that sits between f of a and f of b that hits the breaking point between this non-continuous function. Well, then it's not hitting the curve. There's no way that I'm going to find a c value that can correspond to a k value that resides on the curve. So that is the importance of having a continuous function. The continuous function makes this a possibility. Okay, let's try this and do a problem on it. Verify that the intermediate value theorem applies to the indicated interval and find the value of c guaranteed by the theorem. Here is our function. It looks like it's a quadratic function. And we are going to be concentrating on the closed interval from 0 to 5. This is like our closed interval from a to b that we were talking about on the theorem, where f of c equals 11. So I need to find some c value that comes out with a value of 11. This is my k value that I'm after. So first off, what we have to do in order to use the IVT, the intermediate value theorem, on our problem is we have to prove that the 2 hypotheses are satisfied. So is the function continuous on the closed interval from 0 to 5? Well, when I look at f of x It is a polynomial. And we just talked about the fact that polynomials are continuous everywhere. So I'm going to write, since f of x is a polynomial, then it is continuous everywhere. So I've been able to prove that I have a continuous function on the closed interval from 0 to 5. Second part of the hypothesis, I need to evaluate my endpoints, because now what I need to prove is that k resides between f of a and f of b, or vice versa, that b is lower and a is higher. Let's look at f of 0. So I'm plugging in the left-hand endpoint. Putting in 0, it looks like I would end up with what? 0 squared plus 0 minus 1. So this evaluates to -1. If I put 5 in, I get 5 squared plus 5 minus 1. That's my evaluation of f of 5. 25 plus 5 is 30, so I'm getting 29 on that. Now, does 11 fall between f of 0 and f of 5? And f of c, is it between f of a and f of b? Well, yes, in this case it is, because 11 falls between -1 and the 29 that we just calculated. So this would be true. We hit that. So we've satisfied both of the hypotheses, which means that we can come in with the conclusion of the theorem. We can apply the IVT to find this particular value c that makes 11 out of our function. And the easiest way, let's just take our function, set it equal to 11, because this is our y value, right? Which is really the k value that we're looking at, and solve it. So I'm going to have x squared plus x. I'm going to swing my 11 over, which will give me a -12. Set it equal to 0. And we all know that maybe we should try factoring since it's quadratic, and we can find the solutions to our equation. And this is going to factor into an x plus 4 and an x minus 3. I hope you agree. And that gives me conclusion that I've got x equals -4 or 3. So I get two solutions here. Are they both good solutions? Well, for my particular problem, I'm looking for something on the interval from between 0 and 5. So I'm going to rule out the -4 and keep the 3. So when c equals 3, it's going to satisfy the intermediate value theorem and get a k value of 11. Okay, I think I'm going to stop there, and then that'll leave us number 75 to go through in class before we start working on the homework. And that way you can ask some questions and we can do one of these together. So that is it for this video.